shows that as the fluid moves faster, either its height decreases or its pressure decreases. And in this case, its pressure is lower, and that's what keeps the balloon floating, basically. And yeah. Okay, so the basis of this exhibit is Bernoulli's principle. And basically what that is that it's saying that when a fluid's speed increases, either its pressure or its height decreases. And this comes from Bernoulli's equation, which is in here. And basically it shows the relationship between pressure, velocity, fluid density, and height. And the thing is, for this demonstration, the change in height is essentially negligible when compared to the changes in changes in speed and pressure, which is why those got crossed out, because the difference in y1 and y2 is, we're saying it's negligible. So what we're really saying is mainly the differences between pressure and then velocity of the fluid. So another thing to realize is that since air is not an ideal fluid, Bernoulli's equation technically isn't entirely true for this scenario, but Bernoulli's principle written up here is still, we can still see the trend. Basically how it works and how this beach ball basically stays and, it kind of looks like it's floating, is because the air that's getting blown out is moving at a higher velocity, as we set up here. And its speed increases, higher velocity, either its pressure or its height decreases. We're not paying attention to height, so its pressure is lower, or it's at a higher speed. And that means where it's a slower speed, the fluid has a higher pressure, and that this pressure difference is what causes the beach ball to get blown back into the stream, because the pressure difference, and it goes from high to low pressure, and that's how it continually stays in the stream. Bernoulli's principle in action. Again, that as the velocity of air increases, the pressure decreases, and that's how this paper airplane is able to fly. And if we put it in the launcher, there it is. So this second exhibit is actually also a example of Bernoulli's principle. This one is how basically paper airplanes fly, and the principle is still the same, and that's still what we're focusing on, and that when a fluid speed increases, either its height or its pressure decrease. And again, we're not factoring in height really, because at the moment it's getting lifted. The difference in height is not as significant as the pressure and speed changes. So basically, and this is also how regular airplanes fly, that the air passes over the top of the wing, as shown here, at a higher velocity, and over the bottom of the wing at a lower velocity. And from our principle up here, we can see that when the fluid speed increases, so that's there going over the top, it's gonna have a pressure decrease. So that means there's lower pressure up here, higher pressure down here, and then pressure goes from low to high, and that's what the lift is caused by. It's caused by the pressure difference, and that's how you actually get lift on the airplane. And then it's also or it can be noted that drag is what's actually slowing the paper airplane down, and then gravity, its mg, is what is causing it to fall to the floor as well. So yes, other things to keep in mind. Okay, so you see your frequency for different length tubes, and this, you see, they make different sounds because the length of the tube is different, and it makes has a different fundamental frequency. Yeah. All right, the main topics of this last exhibit are standing waves, resonance, and fundamental frequency. Basically, since these are open tubes, we know they have nodes at the center, and then two antinodes on either side, or either end, rather, of the open tube, and this represents the fundamental frequency, or first harmonic, of that, basically, that for that tube. And while it's important that, or to note that there actually are other frequencies and harmonics, harmonics heard, this is the main one we hear. And so each of those tubes basically had, like it said, a different frequency on it, like a different amount of hertz for different notes. And the one I showed primarily was the one that was for the note E, and that's 82.4 hertz. And yes, this is the equation we need to know. V equals lambda f, which is wavelength times frequency, and that's the velocity of the wave. And so basically, if we wanted to find the length of the tube, there's a couple different things we could use. We use that the speed of sound is 343 meters per second, and then we pop that into equation along with our frequency being 82.4 hertz, and we are solving for wavelength then. Yes, here's where we plug it all in. Hertz is just inverse seconds, so that cancels out the second, and we're left at the wavelength equals 4.16 meters. But since we have to remember, since this is an open tube and this is a fundamental frequency, the tube is actually only 1/2 of the actual wavelength. So if we use that, plug it in to find the actual length of the tube, we have to divide by 2, and so the length of that tube was around 2.08 meters long.